My dear friends, I am Prof B Oza, talking with you since many sessions. We are trying to learn power system protection on YouTube videos, and I have no count, but I think I have given some 50 or 50 plus videos in YouTube about generator protection. I mean about power system protection, in which we have talked about transmission line by overcurrent and earth fault protection, transmission line by distance protection. And we have seen some easy practicals which can be done by the educational institutes and the training centers of different industries, if at all they want to rig up for training their engineers. Right now we are in generator protection, and this is last but one video. That means 10th will be a concluding video. This is number 9. And we have been discussing abnormalities in generator. And today we will be discussing only one abnormality, that is pole slipping protection. As in generator protection 8, in 9, this pole slipping is also very complex. And many dark outs are seen. Cascaded tripping and tripping of a large area, power loss in large area is found due to pole slipping. So pole slipping protection is very important. So to understand, let us see that when the generator is running at full load, it operates at some load angle delta 1, and all the generators are running at that load angle delta 1 because they have to be in synchronism under normal working operation. If the load is abruptly increased or abruptly thrown from one generator, or due to fault somewhere in the power system network, you see the fault will be nearer to some generators and farther from other generators. So generators which are nearer will, their load angle will be much higher than delta 1, and others will be higher than delta 1 but not as bad as that. So all the generators will be running asynchronously, and this is known as pole slipping. We were calling it power swing also. Both are the same terms. Pole slips, that means the rotor falls behind the stator rotating magnetic field. That is what is happening. This asynchronous working generator can take for certain time. That is known as transient stability limit. That you might have learned in BE classes, in stability classes, equal area criterion and many other criterions. There are many other theories which decides for how much time the generator can remain out of step. For how much time generator can work in asynchronous condition. But once it has lost its transient stability limit, then even if the fault is cleared, it cannot regain synchronism. It will come to halt only. And if it comes to halt, that means the speed is reducing badly and the slip is generated. And that slip will harm the rotor. So what happens to the system, that is a different thing. You see that you have learned in power system stability. But what happens to generator? Right now I am in charge of one generator and my generator has lost transient stability limit. So my action is to disconnect my generator from the bus. That is the only thing I can do. Other things I cannot do. So how does the generator sense that pole sleeping? Right? That is very important. So the relay is obviously a two input relay. It is a distance relay and it is fed by CT and PT both. So what kind of protection do we give? Protection usually given is of this kind. I have shown the locus of loss of synchronism, that is traveling from right to left. From right to left. Right. Here the load angle is delta 1. It may be normal operating point, but then as it travels further, the load angle increases, as we have seen in power swing in distance relay chapter. The load angle goes on increasing, and at this point, when it is crossing the directional characteristics, the load angle is 180°. That is two pole pitches. Actually, theoretically, load angle, if it goes beyond 90°, you are already in unstable region. But now, when modern AVRs are available, which can boost the voltage up to twice the voltage, and therefore it will be able to keep the generator under stability condition for three pole pitches. So you can go up to 270 degrees. You can go up to 270 degrees. And here, that blinder characteristic, it comes to 270 degrees. Right. So the scheme is something like that, that when the locus of asynchronous operation or locus of impedance seen by the relay crosses the directional relay, a timer starts and timer should time out before it crosses the blinder characteristic. This is Ohm relay. This is Ohm relay. Ohm relay has an importance here in pole slipping. So it is also known as blinder. So timer should have timed out. It takes few milliseconds. You see, because loss of synchronism means the generator speed is decreasing. Its load angle is increasing. Its load angle will not increase very fast. It depends upon what is its inertia, momentum of inertia. Say, if you have got a 660 megawatt machine, its inertia is very high. That means it can respond to the change very slowly. If fault occurs, it will respond. Its speed will delta will increase, but it will slowly increase. But if there is a 15 megawatt machine, it will go out of step very fast. So it depends, and therefore people now prefer that mostly the machines should be 660 megawatt machines. The era of 210 megawatt machines has gone, and now people are preferring 500 megawatt and 660 megawatt machines. So timer times out before this, and when the characteristic crosses this, class A protection is initiated. Class A protection is initiated because pole slipping is class A. It is going to damage the rotor very badly. Therefore, it is class A protection. The control circuit is something like this. We have an overcurrent starter. Then this characteristic A, as you have seen, is a characteristic A is a directional characteristic and characteristic B is a blinder characteristic. So when the impedance seen by the relay crosses A1 will operate. B has not yet operated because characteristic has not crossed blinder, so B1 is closed. T3 is open because T has not energized. But when A1 operates, T is energized. What is this OC1? OC1 is overcurrent starter. and usually set at rated current of the generator. It is used because while starting and stopping, you are already under pole slipping condition. And the relay should not give a trip command when you are starting and stopping the generator. But when you are starting, the rated current is not there. Current is zero. Therefore, OC1 is not operated. And while you are stopping, then also OC1 is open. It is closed only when the generator is normally running. So C1 is operated, A1 is operated. Therefore, timer is energized. Timer will time out before the characteristic crosses B. I told you. Please remember. Little complex protection. Timer will time out before characteristic crosses B1. So when the timer times out, T1, T2 and T3 will operate. T3 will keep the timer energized, right? Because if timer de-energizes, then T will de-energize. So T3, because B1 is going to operate afterwards. So T3 is a hold-on circuit. T1 and T2 prepares the trip and alarm circuit. Now the impedance seen by the relay will cross B. Impedance seen by the relay will cross B. So when it crosses B, what happens? B1 and B2 are energized. B1, B2 and B3. B1 will open out. Well, but T is yet energized because of T3. B2 and B3 will give alarm and class A trip. This is the DC control circuit of pole slipping protection. Very interesting circuit. And the relay is very costly also. We had purchased the relay in a very good amount, beyond 50 lakhs or something. Relay is costly because it has to be very sensitive, right? And it has to measure very small time, because timer is set for hardly 5 or 6 milliseconds. So it is not like 10 seconds or 60 seconds or something. So timer is very important, and the characteristic A and B are also very important. So how to set this relay? That we will try to see. Generator rating is 210 megawatt, 9050 amperes, 247 MVA, 15.75 kV. Transient direct axis reactance is 30.5. Subtransient direct axis reactance is 21.4. Generator transformer rating is 250 MVA, 15.75 is to 240 kV. Percentage reactance of the transformer 40%. System fault level is 10,000 MVA. CT ratio that you are using at generator terminal, because 9050 amperes is current, CT ratio is 10,000 by 5. PT ratio is 15.75 kV is 210 volt, because PT is also at the generator terminal. The rate of slip is 1600 degree per second. That you have to ask the generator manufacturer at what rate it will slip. So he has given 1600 degree per second. System impedance angle is 75 degree. That is the line. The system is at 75 degree. Generator pole slipping. Now you have to refer to the figure that we will see in the next page. Generator pole slipping reactance OA. OA. Let us see what is OA. OA. That is reactance, pure reactance. Because PT is on the generator terminals, reactance is seen behind the relay. So OA is seen behind the relay. That is generator pole slipping reactance that you can plot, right? You can calculate in ohm from percentage that is given. You can take either subtransient or transient direct axis transient reactance, and you can plot OA. That is the generator pole slipping reactance as the pole is. And that is equal to, yes, it is given, I'm sorry, it is given 90% of subtransient reactance. Usually, this is what is taken. And from 21.4, I am converting to kV square by MVA. I am multiply to convert it in ohms because I will have to plot ohms. So I plot 0.193 ohms to some scale. So you have to draw this diagram to scale. So please remember that. Plot this diagram to scale. OA is 19.4. Then next what you have to plot? What next you have to plot is transformer reactance because transformer reactance is in forward direction. So from 14, I am converting it to 15.75 kV because generator terminal relay is there on 15.75 kV side. Transformer MVA is 250. So 0.1389. So we plot OB at OB 0.1389. You can see OB. O is the relay location. OB because it is in forward direction. BC is source reactance. BC is source reactance. So BC is source reactance. So what is source reactance? kV square by MVA into 15.75 kV square divided by 10,000 because system fault MVA is given to be 10,000. So 15.75 kV square divided by 0.0248. So BC that you have plotted it as an angle because your system angle is 75 degree. BC to scale is plotted. Now AC is your line and perpendicular bisector of AC is going to be a locus of pole slipping. That is shown. Perpendicular bisector of AC is pole slipping locus. Now, what are the settings that you have to find? Directional characteristic. You have to tell at what angle you will keep. Usually at 75 degree because 75 degree happens to be the line angle, transmission line angle. So we will plot the directional characteristic passing from O at 75 degree to R axis. X-axis is resistance axis and Y-axis is reactance axis. So we plot the directional characteristic, right? So draw OA to scale and then plot the directional characteristic. So we plotted the now what we have to find, that means you should know that 75 degrees is the angle that we are deciding. Usually we take 75 degrees. So that first thing that you have to tell to the person who is setting the relay that you will plot directional relay that is obviously passing through and at 75 degrees. So one can easily plot. You can plot geometrically. Then you have to find out the negative resistance reach, that is 0.173. So how 0.173 is calculated? So that is calculated as I told you AC. Perpendicular bisector to AC is pole slipping locus and we can slip up to 270 degree. Delta 4 is 270 degree. How to find out the 270 degree? That is our point. So pole slipping locus you can, draw the line on both sides, right? And then AC as a diameter, you draw the half circle which cuts the pole slipping locus at N. So you got N. And that O to N is what you have to give because that is to be set. And blinder characteristic you have to pass from N at 75 degrees. So blinder characteristic is also at 75 degree and negative resistance reach by scale that you have selected is 0.173. So this is how you can set this pole slipping relay. Geometrically, you have to plot. Geometrically, you have to plot. So that is the pole slipping relay, right? So solve what we have. Directional unit, draw directional unit passing through origin at an angle 180 degrees. It is 75 degree. It should be 75 degree. 750 is the typographical error. 75 degree to resistance axis. That's what I told. And from there we found out delta 3 is 183.5. So delta 3, if you see, is uh, delta 3. I show once again. Delta 3 is AM and C. AMC is little more than 180 degree, because it's little more than 180 degree. When it is crossing the pole shaping locus is crossing the directional. And when it is crossing the blinder, it is 270 degree. And we have to keep 270 degree because with modern auto reclosers, up to 3 pole pitches it is allowed. So you have set delta 3, and but timer should have timed out by that time. If timer has not timed out, you see, if there is something else, then timer will not time out and characteristic will cross blinder. If timer has not timed out and characteristic crosses timer, then tripping will not occur, because timer is also in the trip and alarm circuit. So because of any other cause than asynchronous working, the mal tripping will not occur. That is taken care of. So that is how you can work against, or you can protect against the pole slipping. I am protecting my generator. I am disconnecting it from bus. If fault is yet there, some another generator will also trip. Like that, many generators will trip. That is what happened in 2012 when the eastern grid, northeastern grid and northern grid, some 22 states were suffering from loss of power. It started from load encroachment and ended with pole slipping. So that way pole slipping is very important. So friends, with that point 173 I could find out, right? Point 173 I could find out. See, OD I could find out point 173. And primary, it is in primary. So you have to change into secondary because relay is in the secondary. So into CTR by PTR. So 2.4156 secondary. And what is timer setting? Timer setting is 54.06 millisecond. How we have arrived at 54.06? 54.06 is delta 4 minus delta 3, because it is passing from delta 3 to delta 4. Directional relay is crossed at delta 3. Blinder is crossed at delta 4. 270 minus 182.5 divided by rate of slip. So that is the time setting. Before that, 54, that means you should, set somewhere at 50 millisecond. That means timer would have timed out, right? So that is how you set the timer. So you will have to set the directional relay characteristic, the angle you have to tell, blinder you have to plot, the angle you have to tell, negative resistance reach you have to tell, the timer setting, and you have to set the overcurrent starter. Usually we set at 110% of the rated current, because 110% it should take continuously. So that is 99.5%. We set 100%. We set the relay at 5 ampere. So setting of overcurrent starter is at 5 ampere. So many settings are there. Again, starting directional relay and its angle, blinder and its angle, negative resistance reach. Number 3, timer setting and overcurrent. 5 settings are to be done in the relay. So that is how it makes the calculation complex. I'm not being able to teach these things to the students because students nowadays do not want to go to this depth. Reason I am failing to understand. Because recently I have got an offer from Adani that they are recently taking some 1,000 GETs, graduate engineer trainings, and they want persons for teaching them so that they can work in Adani atmosphere. So when I go there, I will have to understand the Adani atmosphere, what is the syllabus. But then the first thing I will have to understand is that those who are coming are ready to go to depth or not. Usually, at least students are not ready to go to depth. Now, those who are now supposed to work in Adani, I hope they will be forced to understand to the depth any subject. But what is the syllabus, etc., I have not yet come to know. But this is what can happen. This is what can happen. Students are not ready to go to this depth. Anyway, but I am putting these videos on YouTube, and I would request you to stay tuned with Me. Let the name of Me go to billions of engineers. And as I'm telling every now and then, I'm getting likes and appreciations from engineers from Pakistan, Oman, China, Korea, India, obviously, and Middle East countries, UK. You see, I don't know the name of the countries because the name of the person lets me know that he is not an Indian. Right? So, and even if he is an Indian, if somebody from Bengal who's not knowing me, somebody from South India who's not knowing me, if he likes, my students will like me. That is, I have from 1988, my first student passed under me, and from 1988 to 2012, I served, and some 1,600 students are very much loving me. So that is no point. They are trying to spread the name of me, but 1,600 is not enough. I want to reach to billions of engineers, and therefore you are needed. The viewers are needed. So friends, thank you for patiently hearing me, and good day.